I left off in the discussion of mean squares by talking about the ratio of two mean squares, mean square model and mean square that residual, that actually provide us an F statistic. And so if the model is worthless, I said we expect the F to be near 1 because the mean square for the model and the mean square for the residual are both estimating error variation. If the model is valuable, then the mean square residual continues to estimate error variation, but the mean square for the model is estimating error variation plus the effectiveness of our model. And so we expect it to be greater than 1. So in class last time, I actually showed you some F distributions. Let's take a look at one right now and use this context to explain it a little more. Actually, let me go ahead and clear that out, and let's just look at one distribution instead of a couple. Okay, so what is this a distribution of? This is a sampling distribution. You know that we create sampling distributions by taking repeated samples. So if we sample over and over and over and over again, and each time we calculate this ratio here, the mean square for the model divided by the mean square residual, and calculate the F. And if the model is totally worthless, then this is the picture that we're going to get. That is, we're going to have a lot of values here between 0 and 1. And then as we get beyond 1, we have fewer and fewer and fewer. So you can see it is possible that we could get a value of 3 even if the model is worthless, but it's not very likely that we'll get a value greater than 3 if the model is worthless. Those of you who have had R in the past might remember that we use the functions p-norm and q-norm, pt and qt. Yes, indeed, there are functions pf and qf. So if I were to take, for instance, the probability on an F distribution of getting 3 or beyond, I would have to enter in 3, but I'd also have to enter in the degrees of freedom for the F distribution. Now this one up here, I notice just from my code that I use 3 and 10 degrees of freedom. So if I enter that in, whoops, oh, I capitalized the F and it's not capitalized in R. That tells me that the area up to 3 is 0.92, so the area beyond 3 would be 0.08. So past this 3 is 8% of the area. That means even if the model is worthless, the possibility of me drawing a sample at random, that will give me a mean squared model over a mean square residual, that F ratio that's over 3 is going to be about 8%. This is the way we do all hypothesis testing. If we set our value to be, hey, I don't want to go beyond 5% error rate, then in fact, let's do a QF, and let's give 0.95. So from 0 up to whatever value it is, we want to have 0.95% of the area. It's 3.71, so right about here. So if we get an F that exceeds 3.71, it's still possible if the model's worthless, but what we're probably going to say is because that F is going to get big when the model becomes more valuable, that we don't think we just had this weird thing happen to us. Okay, sorry, I paused the video because I just got a phone call, and so I'm not exactly sure where I was, but let me go ahead and continue. So I was looking back here, I think, at this F curve and saying, look, it's possible to get values way out here near 4 or even beyond. when the model's worthless. But what we do in hypothesis testing is set that possibility so low that if we do get out there, we're going to take the other alternative, which is the model is valuable. And so if the model's valuable, we expect the F to be greater than 1. And in fact, if you look at this ratio, the more valuable the model is, the higher our mean square model, the smaller our residual, the bigger F becomes. Remember when we were dealing with sums of squares, that if we took sum of squares for the model divided by sum of squares residual, that is actually telling us that we have that much variation accounted for by our model. That's our R squared, our coefficient of determination. So all of these things tie together. All of them come together. So let's look at an example. I'm going to go ahead and take the police funding model that I ended up with. I think a lot of you did too. Just to review, it's the model with no high school, college, and college grads. And so let me go ahead and get the summary of that particular model. Let me go ahead and clear out that plot. We don't need to be looking at that. Let me get the summary of that model. All right, so when I look at this, I see it accounts for about 28% of the variation. That is the sum of squares model over sum of squares residual is 0.28, 28% of the variation. But you'll also notice here that I have an F ratio, an F statistic. That F statistic is 5.83. Now that has 3 and 46 degrees of freedom. So here, this is kind of cool. Let's call this F distribution up. And what was it again? It was, oh, here it is, 3 and 46. So let me change this from 3 and 10 to 3 and 46 degrees of freedom. And run this plot. So this is the way it would look, okay, like this. And so if we get a value out here, we're going to reject the null hypothesis that the model is worthless. Well, what did we get? We got 5.83, 5.83. So if I look at this F distribution, it's out here off the chart. Is it possible that we would get that just from our random sampling? Yes, it's possible to get a sample like that, but 99.9% of the samples are less than that. And so it's more likely that we're in this situation here where the model is valuable. And when the model is valuable, the mean square for the model goes up, just like the sum of squares for the model goes up. The F ratio, mean square model over mean square residual, that F ratio goes up, and we end up with a large F. So that's what I think is happening. If you look at the possibility, if the model was worthless, the possibility of getting a value as high or higher than 5.83 is 0.0018. 0.0018. Okay, so therefore I'm going to reject the null hypothesis that the model is worthless, and instead I'm going to go with that the model has some value. Now, let's see, what else can I tell you while we're at this? Oh, here's one other thing that's kind of interesting. If we were to take the mean square residual and take the square root of it, let's go back here. Remember mean square, sum of squares are degrees of freedom, that if you take the square root of it, you get a standard deviation. Well, what if you take the mean square residual based not upon taking y deviation from the mean, but y deviation from predicted scores and take the square root of that? Well, that's a sort of standard deviation as well, and we call that the residual standard error. So that's what this 12.14 is. Oh, I know what else I can tell you. Where's that 3 and 46 degrees of freedom come from? So let me go back here to this F statistic. So The numerator degrees of freedom for an F statistic are the degrees of freedom for MS model. Degrees of freedom for MS model is the number of predictors in the model. So let's look back here. How many predictors do we have? We have 1, 2, 3. No high school, college, and college grads. So there is 3 degrees of freedom. We call it the numerator degrees of freedom because it goes with the mean square that's in our numerator, the mean square model. The degrees of freedom for mean square residual is sample size minus number of predictors minus 1. Okay? Sample size minus number of predictors minus 1. Let's go back and look. Our sample size was 50. We have 3 predictors. 50 minus 3 is 47, minus 1 is 46. So that's how we get the degrees of freedom. That's called the denominator degrees of freedom because it's the degrees of freedom for mean square residual. One other cool thing, let's say we're not doing regression, so we have no predictors. If we have no predictors, look what this turns into. Sample size minus 0, minus 1, or just n minus 1. And n minus 1 was where we began when we were talking about how to get the mean square. We take the sum of squared deviations about the mean, divide it by n minus 1, and of course if we take the square root of that, we get the standard deviation.